The objective of this lesson is to create equivalent fractions using linear models and to relate the models to mathematical equations. In previous lessons, students have learned about equivalent fractions. In this lesson, we will represent equivalent fractions using linear models. We will then relate the models to equations. Let's first look at some fraction strips. These strips represent multiple fractions in their relationship to the whole. Notice it has 2 1/2 fractions, 3 1/3 fractions, 4 1/4 fractions, and so on. In this way, it is easier to see how the number of pieces needed to create the whole is represented in the denominator of each fraction. In some ways, fraction strips are related to a fraction number line. The strips are divided into equal pieces just like the marks on a number line. They are each labeled differently, however. The fraction strips are labeled for the unit fraction represented, while the marks on a fraction number line are labeled to represent the distance each mark is from 0. If we cover the fraction strips at the 1/2 mark, we can begin to see which fractions can be iterated as equivalent to 1/2. For example, 2/4, 3/6, 4/8, and so on. Looking at 1/2 and 2/4, notice it takes 2 1/4 size pieces to create 1/2. In other words, it takes 2 times as many 1/4 size pieces to be equivalent to 1/2. We can represent this by multiplying the numerator of 1/2 by 2. Similarly, it takes 2 times as many 1/4 size pieces to create a whole. We can represent this by multiplying the denominator of 1/2 by 2. We can create an equation showing the relationship between 1/2 and 2/4. Next, 1/2 is the same as 3 1/6 size pieces. It takes 3 times as many pieces to create the whole, and 3 times as many pieces to make a fraction equivalent to 1/2. We can represent this relationship as an equation as well. Let's now extend this process to represent fractions equivalent to other values. For example, fractions equivalent to 2/6. In this case, 1/3 and 4/12 are both equivalent fractions. 2/6 is the same as 4 iterations of 1/12. It takes 2 times as many 1/12 size pieces to make a whole, and 2 times as many 1/12 size pieces to make a fraction equivalent to 2/6. Here is an equation to represent this. Next, the relationship between 2/6 and 1/3 is slightly different. Rather than using multiplication, we need to use division. It takes 3 1/3 pieces to create the whole, and 6 1/6 pieces. Half as many pieces the size of 1/3 are needed to create the whole. This is represented by dividing the denominator by 2. Also, since thirds are twice as large as sixths, half as many thirds are needed to represent the same amount as 2/6. This is represented by dividing the numerator by 2. We can also identify the relationship between equivalent fractions using a number line. This is a number line representing 4/6. To discover equivalent fractions, it is helpful to see if the number line can be repartitioned into larger or smaller equal pieces. In this case, we can do both. Larger pieces would be thirds, and smaller pieces would be 12ths. Looking first at repartitioning the number line into thirds, we can visually identify the relationship between 4/6 and 2/3. Using thirds, only half as many partitions are needed to be the same length as 4/6. We can show this relationship in an equation. Repartitioning the number line into 12ths, we created twice the number of 1/12 size pieces as we had 1/6 sized pieces. Because twice the number of 12ths are needed to create the whole, twice the number are also needed to make a length equivalent to 4/6. The equation looks like this. The objective for this lesson was to create equivalent fractions using linear models and to relate the models to mathematical equations. We met this objective by using both fraction strips and number lines. We identified equivalent fractions and saw how the relationship between the quantity and size of equivalent fractions can be expressed using multiplication or division.